And also, fortunately, it's within the wavelength that I hear. All right, so my frequency is going to be 320 hertz. What I want to do is figure out where that first harmonic is. At what point am I going to get an antinode and a node? Now, it helps on this demonstration as well as on the lab associated with it that we kind of know what the answer is roughly. So I'm going to do just a quick figure in right here. All right, so I expect it to be somewhere around 25 centimeters. Now, an odd thing that I haven't quite figured out whether it was done on purpose. It was done consistently. Now, on the side of this, there's measuring tape so that you know what the height is. Unfortunately, all the zeros starts 2 centimeters from the top. And that was consistent across the board. And I thought there was a justification for it, but I'm not convinced there is. Now notice the water level. I'm hoping you can see the water level here. I guess Sushil, no, I guess Doris, you're the farthest away. Can you see the water level? Okay. Now I can adjust the water level just by moving this. As I move it up, the water level will rise. Matter of fact, it will rise until the level here is equal to the level here. So the level inside. So I can make this go up just by adjusting that. Also helpful on this is sometimes I have a trash can nearby. And now we'll hit the, let's bring the trash can in for now. In case I have to do a very sudden dump of water. All right, so I'm going to lift this. I've gotten better, not 100% yet. As I lift it, this is metal scraping on metal. Sometimes it's a very harsh noise. All right, not that time. All sorts of wonderful crud floating around in the water there. Shouldn't affect it because what we really care about is the length of the air here and not the length of the water. All right, so when you're striking a tuning fork, I used my finger before, that's fine. Some people will take it and they'll just bang it on a hard object. You do get a nice loud sound, but if you look at especially the older ones, there are dings all along it because of people banging on hard objects. So you should hit it with a soft object, and thus we have the stopper and rod. So the sound is going down, hitting the bottom, and bouncing back. Now, when we get to our antinode, when we have an antinode at the top, remember that this is where we've got the biggest difference in pressure, because we're dealing with sound. And biggest difference in pressure, we will take as a louder sound. That far down. All right, so we'll start it up here. I loosened it too much there. All right, so I assume you heard the slight change. That's the harmonic. It's right there when I did it. and that's about 23.4 centimeters. Unfortunately, it's a clear tube and I can see through it. So based on here, it was 23.4. Plus the 2 centimeters at the top, that from where 0 was, plus 2. So I get 25.4 centimeters. And that's supposed to be an M there, centimeters. All right, let's figure out what the speed of sound is based upon this rough experiment. This should be the quarter of a wavelength. That should be, that's the first harmonic, that should be 1/4 of the wavelength. Therefore, what is the wavelength? Or how would you find it? Multiply by 4. Yep. Multiply both sides by 4, and we get 101.6 centimeters is the wavelength. I know what the frequency is. I know what the wavelength is now, but we want that in meters, of course. And so I know that the speed of the sound was frequency times wavelength, which is 320 hertz, times 1.016 meters. And we get
325.12.
One more time.
325.12.
325.4.
12.
Units?
Meters per second.
Yes. Now the speed of sound, there's a formula for it, required knowing the temperature in the room, but the speed of sound at what's generally considered room temperature, 25 degrees Celsius, is about 340 meters per second. So we're off by 15 meters per second out of 340. So that's looking for around a 5% error. So the percent error, 340 minus 325.12 divided by 340 times 100%. Yeah, let's find out the actual number.
.37% to 38.
All right, under 5%. That's worth rejoicing internally. All right. Now, given this, well, actually, let's predict where the next harmonic is. Yes, Cassandra.
How did we get the 340?
I just basically said that's the speed of sound.
Okay.
It's ish. Speed of sound is temperature dependent, and so it would require knowing the temperature in the room. All right, I would expect the next harmonic to basically be 3 times this one, so the next harmonic should be somewhere around 75 centimeters. So I would expect the next harmonic to be somewhere in this region right here. This is probably going to require a dumping of water. Let's see. There we go. I don't know if you were, I'm standing right next to it, so I heard something, but okay. As I have identified roughly where it is. So my finger's at just under 78 centimeters. So we'll go through the similar process. This is the third harmonic. So 3/4 of a wavelength, I think I said just under 78 centimeters, so 0.7, then I'm going to add the 2 centimeters from the top, 0.798 meters. So that was from 77.8, just under 78, plus the 2, 79.8, and then move the decimal point over 2 spaces. All right, so that's 3/4 of the wavelength. So what is the wavelength? Hopefully it's somewhere around there, but probably going to be a little bit off. Or how would you find it?
Multiply both sides by 4 and then divide by 3.
Okay. That's one way of doing it. You can multiply both sides by 4/3, multiply by 4, divide by 3, and you get 1.061. 1.064.
Yeah.
Meters, which is not too far off. It's 4 or 5 centimeters off what we had before. So the speed of the wave should be the frequency through trusting the manufacturer, 320 hertz times 1.064 meters. We should get closer to 340, I believe.
$340.48.
340.48?
Yeah.
Woo! Pretty darn good there. Now properly, just like with the previous experiment, to do it properly, there's going to be some inherent error in it, and so you would for this we would find several standing waves with varying masses at the end. For this one, we would try various frequencies and just to balance errors out. Any questions there before we do 2 free ends? Because we are about to predict that frequency. And either I'm spilling it or there's a small leak in this. All right, 2 free ends. By the way, when I was filming this lab during lockdown, probably the most profanity I had to edit out. I went for a longer string so it's easier to get the larger harmonics. But I had so much mass on it for the first harmonic that the string broke and then the pulley came off and then it turns out that the frequency of the string vibrating was very similar to the frequency of the shutters on the camera I was using on that camera. So watch the video, it looks like the string's not moving at all because the string basically was back in the same place again by the time it took the next picture. I wasn't redoing it at that point. All right, 2 free ends. Because both ends are open, we have 2 free ends. The first harmonic, well, a free end is an antinode. And the simplest one is that. I got an antinode at each end. As I'm doing this, as I'm swinging it around, there should be a dead spot, a silent spot in the middle. Unfortunately, to test that would require disrupting it, and it would no longer be there. The second harmonic, again, I have to have a free end. It's an antinode, so I have to have that at the end. Oops, I went too far.
So this time that'd be second instead of third?
Correct. It's only the one free, one fixed that it just does the odds. Yeah. Well, I'm not going to get much better. All right, so let's start trying to figure out how many wavelengths this is. Again, a full wavelength, that's a full wavelength right there. So on that first one, how many waves is that?
Half.
Yes, because we're basically going from here to here. We're chopping off the quarters at the end. So this is half a wave. Supposed to be a lambda. How many waves is this? And remember, we're at a half wave every time.
One?
Yes, it's one wave.
One and a half. 2, sir.
All right. Given our speed of sound, we'll stick with the 340 for now. I know speed is equal to frequency times the wavelength. If I work under the assumption that the speed of sound in this room at this moment is 340 meters per second, that's equal to the frequency that we will hear times the wavelength. Well, we need to figure out what the actual value is. I know that the first harmonic is a half a wave, and basically that's the length of the tube right there. I'm going to stretch it some because as I swing it, it does stretch some. And 84 centimeters. So I guess in terms of what we have right here, the distance from here to here is 84 centimeters, or 0.84 meters. Since that first wavelength is a half of a wave, since the first harmonic's a half a wave, I got half of a wave is equal to 0.84 meters. Therefore, what is the wavelength? All right, so 1.68 meters. So therefore the frequency is, if someone figures that out, I need to get back to, there we go. It's going to go through its bit. So what is the frequency?
202.38.
200,
2.
202.58?
38.
38. Units?
Meters per second.
Hertz. The meters per, notice that from the unit point of view, we have a meters per second, and then we divide by a meter. Dividing by any fraction is the same as multiplying by the reciprocal, so that would be meters per second times, well, actually, let's write it as a division, divided by meters, which is meters per second times 1 over meters. Meters cancel out, and I'm left with 1 over seconds, which is a hertz.
How did you get the 1.?